There is a light arriving at our planet right now that left its source before our Sun existed. Before the Earth had cooled from its formation, before any eye had ever opened in the darkness to look up at anything at all, that light has been travelling for 13,300,000,000 years, crossing distances so immense that the very language of numbers begins to fail us. And when we finally built a machine powerful enough to catch it, a golden mirror folded into a rocket, launched on Christmas morning into the cold of space. What we found on the other end was not what anyone predicted. The galaxy is called JWST 40. It is the most distant structure humanity has ever confirmed, and it should not exist, not like this, not this size, not with these elements, not with this many generations of stars already dead and recycled inside it. At a moment in cosmic history, when, according to our best models, the universe had barely begun to breathe, how did something so large get built so fast? Why does it already contain oxygen? An element that requires multiple stellar generations, each burning for millions of years, to manufacture. And if this galaxy shouldn't be here, what does it mean for every equation we've written about how everything came to be? These are not small questions. They are the kind of questions that keep astronomers awake at 3 a.m, staring at data that refuses to behave the way the textbooks say it should. This is the story of what we found at the edge of time, and why finding it changed something fundamental about the way we understand everything that came before it. There is a model that cosmologists trust more than almost anything else in science. It is not a simple model. It involves matter we cannot see, energy we cannot explain, and a force of expansion that has been accelerating for 5 billion years without a known cause. But it works. It works with extraordinary precision. It matches the distribution of galaxies across billions of light years. It predicts the temperature of the afterglow of creation to within fractions of a degree. It accounts for the ratios of hydrogen to helium forged in the first 3 minutes after the Big Bang. By almost every measure we have ever devised, it is the most successful physical theory in the history of science. It is called lambda CDM, lambda for the cosmological constant, the term Einstein added to his field equations in 1917, then called his greatest blunder, and which was quietly reinserted into the mathematics in 1998, when 2 teams of astronomers looked at distant supernovae and discovered, to their collective horror, that the expansion of the universe is not slowing down but speeding up. CDM for cold dark matter, the invisible non-luminous, gravitationally active substance that comprises approximately 27% of all the energy in the cosmos, that has never been directly detected in any laboratory on Earth, and without which no galaxy would ever have formed, because the ordinary matter alone would not have had enough gravitational pull to collapse into the structures we see. Lambda CDM is, in essence, a description of a universe whose 2 dominant components are things we have never directly observed, and yet it works. That is the maddening, glorious, slightly unsettling truth. Here is the story the model tells. 13.8 billion years ago, in a moment of infinite density and temperature that our mathematics cannot describe, everything began. In the first seconds, the universe was a plasma so hot that no atom could exist. Protons, neutrons, electrons, photons, all colliding in a roiling soup that was simultaneously everywhere. As it expanded and cooled, the first light nuclei fused. Hydrogen, deuterium, helium, a whisper of lithium. After about 380,000 years, the universe had cooled sufficiently for electrons to combine with protons for the first time, forming neutral hydrogen atoms. This moment is called recombination, and it is the moment the universe became transparent to light. The photons that were released at that moment, the flash of a universe finally becoming see-through, are still travelling through space today, cooled by 13.8 billion years of cosmic expansion to a temperature of just 725 Kelvin. We detect them as the cosmic microwave background, and they are the most ancient thing we have ever measured. For the several hundred million years that followed, the universe was dark, not the romantic darkness of a cloudless night sky, the sort of darkness that contains stars and galaxies and the Milky Way arching overhead, No, this was a total darkness, unbroken and absolute, in which the only structures were slowly growing concentrations of neutral hydrogen and dark matter, clumping together under the relentless tug of gravity. Astronomers call this the cosmic dark ages, and it is one of the least understood epochs in the entire history of the universe. We have almost no direct observational data from it. It is a void in our knowledge, as complete as the void in the sky above it. Then something happened. The hydrogen clouds collapsed, the first stars ignited, and the universe, after hundreds of millions of years of darkness, blazed back into light. The Lambda CDM model makes a very specific set of predictions about how this happened. It predicts that the first structures to form were small, clumps of dark matter with masses comparable to 1 million suns, called mini-halos, which then assembled gradually into progressively larger structures through a process astronomers call hierarchical assembly. Small things came first. Medium things were assembled from small things. Large things accumulated last of all. The universe in this picture is built from the bottom up, the way you might assemble a city, not by conjuring a skyline whole, but by first building a single house, then a street, then a neighbourhood, then, over centuries, something resembling a metropolis. This hierarchical structure formation is one of the most precisely tested predictions of the Lambda CDM model, and it matches, with remarkable fidelity, what we observe in the universe around us today. The cosmic web, the vast filamentary network of galaxy clusters, separated by enormous voids, is exactly what Lambda CDM's equations predict it should look like after 13.8 billion years of gravitational assembly. The large-scale distribution of matter, traced by galaxy surveys containing hundreds of millions of objects, matches the simulations with almost eerie precision. When theorists run computer simulations of the Lambda CDM universe, starting from the slight ripples in the cosmic microwave background that seeded all subsequent structure, they produce something that looks, to a startling degree, like the universe we actually live in. The key word in that last sentence is today. When we test Lambda CDM against the universe as it exists right now, or as it existed 1 billion, 3 billion, even 8 billion years ago, the model holds. The problems begin when you look further back in time. Much further. To understand why, you need to understand what astronomers mean when they talk about looking back in time. When you look at a star in the night sky, you are not seeing the star as it exists in this moment. You are seeing it as it was when the light you are now receiving first left it, which, for the closest stars, is just a few years ago, but for the stars in distant galaxies is billions of years in the past. Light travels at 299,792.458 kilometers per second, which sounds incomprehensibly fast, until you remember that the observable universe is 93 billion light-years across. The further away an object is, the further back in time you are looking when you observe it. Astronomers quantify this distance using a property of light called redshift. When a source of light is moving away from you, the waves of light are stretched to longer, redder wavelengths, the same principle that makes a passing siren drop in pitch. In an expanding universe, almost everything is moving away from us, and the further away it is, the faster it moves. This means the light of distant galaxies is redshifted, stretched toward the infrared end of the spectrum, and the magnitude of that stretch, expressed as the dimensionless number z, tells us precisely how much the universe has expanded since that light was emitted. A galaxy at a redshift of z equals 1 emitted its light when the universe was half its current size. A galaxy at z equals 5 emitted its light when the universe was 1/6 its current size, and a galaxy at z equals 14, the kind of galaxy that the James Webb Space Telescope has now confirmed the existence of, emitted its light when the universe was a tiny fraction of its present scale, a mere 290 to 300 million years after the Big Bang, 300 million years after the beginning of everything. That is the epoch we are now able to observe directly, for the first time in human history. And at that epoch, according to the Lambda CDM model, galaxies should be tiny, sparse and fragile, infant structures of perhaps a few tens of millions of solar masses, still assembling their first generation of stars far too young to have built the kind of complex, metal-enriched, heavily populated stellar ecosystems we associate with mature galaxies in the universe we inhabit. The model is not being unreasonable when it predicts this. The logic is sound, the physics is well understood, and the timeline is not guesswork. It follows from first principles, from the measured density of matter in the early universe, from the rate at which dark matter halos could grow at those cosmic epochs, from the physics of how gas cools and collapses into stars. According to every well-tested tool in the theoretical cosmologist's arsenal, the universe at 300 million years old should be nothing but small, struggling proto-galaxies, barely visible, barely formed, just beginning to write the first sentences of a story that would take billions of years to complete. That was the expectation. That was the prediction. That was, for decades, the consensus that shaped how we designed our telescopes, what targets we chose to observe, and what we expected to find when we got there. And then the James Webb Space Telescope opened its eyes. The first scientific images from JWST were released on the 12th of July 2022, and they were not merely beautiful, they were immediately, viscerally surprising. The deep field image, a region of sky so small you could cover it with a grain of sand held at arm's length, was packed with galaxies, thousands of them, at all distances, at all stages of development, galaxies whose light had been travelling for billions of years. And scattered among them, visible to trained eyes almost immediately, were objects that should not have been there. Objects that were too bright, too red, too far, too large, and in some cases, as we would soon discover, too chemically evolved to be compatible with the neat, hierarchical bottom-up story that Lambda CDM had been telling us for 30 years. This is, to my mind, one of the most consequential scientific situations of the last century. Not because the model is wrong, that question is still genuinely open, and we will come to it in detail. But because we now have, for the first time, direct observational access to the very edge of cosmic dawn, we are looking at the universe when it was a newborn, and the newborn is not behaving the way any of us expected. What precisely did we find? What are these galaxies, and what makes them so difficult to explain? And what, if anything, does their existence tell us about the deep architecture of the cosmos? To answer those questions, we need to go back to the beginning, not of the universe, but of the telescope that is forcing us to ask them. It began, as so many of the most important things in science begin, with a question. Not a comfortable question, not a question that guaranteed a satisfying answer, but the sharpest possible question you can ask of the universe. Can we see the first light? For decades, that question had no practical answer. The first galaxies, if the models were right, would be so distant and so faint that no telescope on the ground or in low Earth orbit could possibly detect them. The Hubble Space Telescope, launched in 1990 and progressively upgraded through the 1990s and 2000s, had transformed our understanding of the universe in ways that remain almost difficult to overstate. The Hubble Deep Field, a 10-day exposure of an empty-looking patch of sky taken in December 1995, had revealed more than 3 zeros and galaxies in a region smaller than 1/100th the size of the full moon. It was one of the most profound images in the history of human civilization, and even it could not penetrate to the very first galaxies, because by the time their light reached us, it had been redshifted completely out of Hubble's optical sensitivity range and into the infrared, where Hubble was only modestly capable. Seeing the first galaxies required a new kind of telescope, a telescope that was large enough and cold enough and sensitive enough to gather faint infrared light from objects 13.5 billion light-years away. A telescope that would not merely be an upgrade to Hubble, but a fundamentally different instrument, designed from first principles around a completely different problem. The instrument that would become the James Webb Space Telescope was first proposed in 1996. Its story between that proposal and its launch on Christmas Day 2021, a story spanning 25 years, 3 major redesigns, a congressional near cancellation, cost overruns that grew the budget from an original estimate of roughly $500 million to a final price tag of approximately $10 billion and no fewer than 20 individual launch delays, is a remarkable human story in its own right, one we will return to. For now, the crucial thing is this. It was designed to answer a specific question. What did the universe look like at cosmic dawn? On the 25th of December 2021, an Ariane 5 rocket lifted off from the Guiana Space Center in Kourou, French Guiana, and carried into the sky the most complex scientific instrument ever launched from the surface of Earth. The telescope was too large to fit in the rocket, in its deployed configuration. Its primary mirror, a mosaic of 18 hexagonal gold-coated beryllium segments with a combined area of 25.4 square meters, had to be folded. Its sunshield, a 5-layer kite-shaped structure the size of a tennis court, made of a material called captan, that had to unfurl perfectly in the vacuum of space without a single one of its 344 single-point failure mechanisms misfiring, had to be folded too. In the weeks that followed launch, NASA's engineers held their breath through 344 deployments that had to succeed without error because there was no backup, no repair mission, no second chance. The telescope was headed to a gravitational equilibrium point called L2, 1.5 million kilometers from Earth, where no human hand could ever reach it. Everything worked. Every fold unfolded, every segment aligned, every sensor cooled to its operating temperature. And in the summer of 2022, the first images began to arrive. What they showed would force scientists to rethink something they had trusted for 3 decades. Let me give you a number. Not an approximation, not a vague gesture at a scale, but a specific number with specific consequences. The galaxy catalogued as JWST 14-0, the current confirmed record holder for the most distant galaxy ever observed, confirmed by spectroscopic analysis in January 2024 and published in Nature shortly after, has a stellar mass estimated at several 100 million times the mass of our Sun. It is 1/600 light-years across. It was detected by JWST at a redshift of 1432, meaning its light was emitted when the universe was approximately 290 million years old, and in that 290 million year window between the Big Bang and the moment this galaxy's light began its 13.4 billion year journey to us, the universe had to somehow manufacture hundreds of millions of solar masses worth of stars, arrange them into a coherent, physically extended structure of measurable size, and produce enough heavier elements, through nuclear fusion in stellar cores and supernova explosions, that we can detect their chemical signatures from across the observable universe. 290 million years is not a long time, cosmologically speaking. For comparisons, the Sun is 4.6 billion years old. The Earth is 4.4 billion years old. Multicellular life on Earth has existed for roughly 600 million years. The universe at 290 million years was younger than the oldest fossils on our own planet. And in that span, it had already produced a galaxy that, in terms of stellar mass, represents a significant fraction of the Milky Way's current total. That is the mass problem. It is not a problem astronomers invented to make headlines. It is a problem that emerges directly from the mathematics of structure formation in a lambda CDM universe. The issue is not just that these galaxies are massive. It is that they are massive at a time when the universe did not, according to our best models, have enough time, enough raw material concentrated in the right places, and enough physical processes working efficiently enough to build them. Here is the physics at the heart of it. In lambda CDM, galaxy formation is hierarchical, and it proceeds through a sequence of steps that each take time. First, dark matter halos must grow by accreting matter from their surroundings. The rate at which they can grow is governed by the underlying matter-power spectrum, the distribution of density fluctuations that emerged from the Big Bang and which we can measure with extraordinary precision from the cosmic microwave background. These fluctuations seed the growth of structure, and their amplitude limits how quickly large, massive concentrations of dark matter can assemble. There is a hard upper limit on how massive a dark matter halo can be at any given cosmic epoch, derived from the statistics of those primordial fluctuations. It is not a soft limit that can be nudged by changing a parameter in a simulation. It is a fundamental constraint built into the initial conditions of the universe. Once a dark matter halo has grown to sufficient mass, ordinary baryonic matter, gas, mostly hydrogen and helium, can fall into it, cool and condense. But this cooling process is not instantaneous. It requires the gas to lose energy by radiating it away, which takes time and which is opposed by all manner of heating processes. Ultraviolet radiation from nearby stars, shockwaves from supernova explosions, the energy released by accreting supermassive black holes. In the standard picture, star formation proceeds at a rate that is limited by how efficiently gas can cool and collapse, and that rate, even at maximum theoretical efficiency, produces a fraction of a percent of the available gas mass in stars per freefall time. Converting gas into stars is, in a normal universe, a slow, inefficient process. The universe is not good at turning gas into stars. It loses most of its potential raw material to heating, to turbulence, to the disruptive energy of the very stars it manages to form. When Ivo Labbe, an astronomer at Swinburne University of Technology in Australia, and his colleague Erica Nelson, then an assistant professor at the University of Colorado Boulder, looked at the very first JWST images in the summer of 2022, they were not expecting to find anything that would challenge these principles. They were hunting for new types of galaxies, objects that Hubble's limited infrared sensitivity had missed. What they found instead was something that stopped Labbe in his tracks. He ran his analysis software on a small red dot in the image. The software returned two numbers: distance, 13.1 billion light-years, mass, 100 billion solar masses. Labbe, by his own account, nearly spilled his coffee. In the Lambda CDM model, a galaxy with 100 billion solar masses of stars at that cosmic epoch, just 700 million years after the Big Bang, somewhat later than JWST 14.0, but still startlingly early, would require something close to 100% of all available gas to be converted into stars. In practice, in every simulation of structure formation that scientists had run, in every observation of galaxy formation at more recent epochs, star formation efficiency never came close to 100%. Typical efficiencies were more like 5 to 20%. The rest of the gas was lost, blown out by stellar winds, heated by supernovae, carried away by the enormous energy outputs of accreting black holes. Getting to 100 billion solar masses in 700 million years would require running that process at near-perfect efficiency, with almost no losses, starting immediately from the earliest possible moment and continuing without interruption for hundreds of millions of years. This does not happen in the simulations. This does not happen in observations of later galaxy formation. This scenario is, to use the blunt language of the theorists themselves, essentially physically impossible within the constraints of standard cosmology. And where there was one such object, there were more. Labbe found 6 candidates in short order. Other teams, working independently on the initial JWST data, found dozens more. By early 2023, hundreds of candidate galaxies had been identified with apparent masses and distances that exceeded what Lambda CDM predicted, not by small margins that could be absorbed by adjusting model parameters, but by factors of 10 to 100 in some cases. The Labbe et al. Paper was published in Nature in April 2023. Its title was characteristically understated, as scientific papers tend to be: a population of red candidate massive galaxies, 600 Maya after the Big Bang. But the sentence that flew around the internet, the one that made it into dozens of news articles and Twitter threads and science podcasts, was Labbe's own description of the moment he first saw the data. "We just discovered the impossible." That phrase deserves unpacking, because impossible is a word that scientists use with great care. What Labbe meant was not that the laws of physics had been violated, nor that the universe had somehow cheated. What he meant was that these objects could not, as far as anyone could tell, exist within the constraints of the theoretical framework that had successfully described the evolution of the universe for the previous 3 decades. They exceeded the dark matter halo mass budget, They implied star formation efficiencies that no known physical process could achieve. They were there, visible in the data, as real as anything we have ever detected, and they had no business being there. This was the beginning of what some cosmologists began to cautiously call the impossible galaxy problem. Others preferred the more clinical term the stellar mass excess. A few, with the kind of dark humour that only emerges in a field when it is genuinely worried, took to calling the most extreme of these objects monsters. The nickname that stuck, however, the one that entered the formal scientific literature with a kind of gleeful precision, was blue monsters. Not because these galaxies were literally blue, though many were bright in the ultraviolet, but because their UV luminosities exceeded theoretical predictions at the bright end of the luminosity function by amounts that could not easily be explained. They were too bright, too massive, and too numerous all at once. Here is why the luminosity problem matters, in addition to the mass problem. In any population of galaxies, the relationship between brightness and abundance follows a characteristic shape called the luminosity function, which describes how many galaxies of each brightness level exist per unit volume of space. At the bright end, the most luminous galaxies, theory predicts a sharp exponential drop-off, a cutoff that reflects the fact that very massive, very bright galaxies are rare because they require enormous dark matter halos to have assembled, and such halos are statistically improbable at early cosmic epochs. This cutoff, sometimes called the Schechter cutoff after the astronomer Paul Schechter, who first characterized its mathematical form, was one of the landmark confirmations of the lambda CDM model in the 1970s and 1980s. What JWST found was that the bright end of the luminosity function at redshifts above 10, the very earliest cosmic epochs, does not show the expected sharp drop-off. Instead, it shows a sustained excess of bright galaxies, a population of luminous objects that, according to lambda CDM, should be vanishingly rare but which appear in JWST data at a rate roughly twice what the model predicts. Not 3 times as rare as expected, not 10 times, twice as numerous. A factor of 2 might not sound catastrophic, but in astronomy, where models routinely agree with observations to within a few percent, a factor of 2 discrepancy in a fundamental prediction is not noise, it is a signal. This is not something that can be explained by measurement error or calibration issues. By early 2024, enough spectroscopic confirmation had accumulated, detailed spectral analyses that pin down the distances to these galaxies with high precision rather than the rougher photometric estimates used in the initial wave of papers, that the broad outlines of the problem were no longer in doubt. The galaxies were where they appeared to be, their redshifts were real, and their brightness, and in many cases their inferred masses, were genuinely anomalous. But here is where the story gets truly complicated, because anomalous does not mean unexplainable. Science does not work by throwing up its hands at a surprising result. It works by proposing hypotheses, testing them against the data, and iterating toward the most economical explanation. And in the 2 years following the initial wave of JWST discoveries, that process generated a remarkable variety of competing hypotheses, each of which illuminates a different facet of what we may be getting wrong about the early universe, and none of which, as yet, fully resolves the tension. The first class of explanations keeps lambda CDM intact and looks for ways to make stars form faster. Perhaps in the early universe, before the interstellar medium had been chemically enriched by many generations of stellar death, before the complex ecology of stellar feedback, winds, radiation, supernovae, had established itself, star formation could proceed at efficiencies far beyond anything seen in the modern cosmos. Perhaps the first galaxies were not subject to the same limiting physics that governs star formation in our own Milky Way today. This idea has been formalized in the concept of feedback-free starbursts, developed by Avishai Dekel and his colleagues at the Hebrew University of Jerusalem, which proposes that in the very early universe, when interstellar gas was denser and more metal-poor, the usual disruptive processes that limit star formation, stellar winds, ionizing radiation from massive stars, had not yet developed to their present strength, and so gas could collapse into stars with extraordinary efficiency, limited only by its own free fall time. The second class of explanations keeps the physics intact but adjusts the properties of the initial stellar population, the initial mass function, or IMF. If the first stars were predominantly more massive than typical stars today, a galaxy could produce far more light per unit of stellar mass, making it appear brighter and therefore more massive than it actually is. A few early universe galaxies that look like they have 100 billion solar masses might actually have 10 billion solar masses, concentrated in stars that are simply far more luminous than the average star in our galaxy. This explanation has the advantage of not requiring any modification to the underlying cosmological model, but it has the disadvantage of being extremely hard to test directly. The third class of explanations is more radical and more uncomfortable. It proposes that the problem is not with how we model star formation, nor with how we interpret the light from these galaxies, but with lambda CDM itself. Perhaps the standard model is incomplete. Perhaps dark matter is not as cold and featureless as the model assumes. Perhaps dark energy is not a constant but varies over time, changing the expansion history of the universe in ways that would alter how much time these early galaxies actually had to form. Perhaps the initial conditions of the universe, the primordial power spectrum of density fluctuations seeded by inflation, contained more large-scale power than the cosmic microwave background data suggests. Any of these modifications could, in principle, allow larger structures to form earlier, resolving the tension with the JWST observations without requiring exotic star formation physics. And there is a fourth class of explanation that has gained significant traction since 2023, one that does not require modifying physics at all, but instead relies on a source of extra luminosity that had been overlooked: active galactic nuclei, supermassive black holes, quasars. This is where the story becomes genuinely strange, because hidden inside some of the most apparently massive of JWST's early galaxies, including many of the original 6 little red dots that Labbe and Nelson identified in 2022, there appears to be something other than just stars. In the autumn of 2023, a team led by Katherine Chwarowski, a graduate student at the University of Texas at Austin, began working through a systematic analysis of some of the most apparently massive early galaxies in JWST's CEERS survey data. Their goal was straightforward: take the brightest, most apparently massive of these early objects, obtain spectra of them wherever possible, and determine whether their luminosities were really coming from stars. What they found was both reassuring and deeply strange. For a significant subset of the most apparently massive galaxies, the ones that most dramatically exceeded lambda CDM predictions, the light was not primarily coming from stars at all. The spectra showed the unmistakable signature of an active galactic nucleus, a supermassive black hole at the center of the galaxy, consuming gas at prodigious rates, generating friction and heat, and producing a blazing continuum of light that could, in many cases, outshine the entire stellar population of the host galaxy by a factor of 10 or more. When Chwarowski and her colleagues stripped the AGN contribution out of the apparent luminosities of these galaxies and recomputed their stellar masses using only the stellar component, the results were striking. The most alarming outliers, the galaxies that had seemed to most catastrophically violate lambda CDM predictions, largely disappeared from the tension zone. Their host galaxies, deprived of the quasar light that had been inflating their apparent masses, turned out to be far more modest structures, well within the range of what the standard model could accommodate. This was, to use Chwarowski's own phrasing, reassuring for lovers of lambda CDM. Stephen Finkelstein, a professor at UT Austin and a co-author on the study, was unambiguous. The bottom line is there is no crisis in terms of the standard model of cosmology, and yet, because the relief was incomplete, and the resolution, if it was one, came with its own set of confounding questions. Because if these galaxies contained active, supermassive black holes in the first 500 to 800 million years of the universe, then the problem had not gone away. It had merely shifted from how did so many stars form so quickly to how did supermassive black holes, objects that themselves take time to grow, come to exist in the very young universe, and how did they grow so large so fast? This is the black hole formation problem, and it is, in many ways, equally as vexing as the galaxy mass problem it was supposed to solve. Here is the challenge. The supermassive black holes we observe in galactic centres today, including the one at the heart of our own Milky Way, called Sagittarius A, with a mass of approximately 15 million solar masses, are thought to have grown over billions of years, primarily by accreting gas and by merging with other black holes over the course of cosmic time. The largest supermassive black holes known, the monsters at the centres of quasars in the distant universe, have masses exceeding 10 billion solar masses. Even assuming they began accreting at the maximum theoretically possible rate, the Eddington limit at which radiation pressure from the infalling material exactly balances the gravitational pull, it would take at minimum hundreds of millions of years to grow a black hole of even 1 billion solar masses from a typical stellar mass seed, except we now know they existed earlier than hundreds of millions of years. We know they were already large, potentially already enormous, in some of these early JWST galaxies within the first 500 million years of the universe's existence, which means either the seeds from which they grew were not the stellar mass black holes produced by the first generations of dying stars, but something much larger, direct collapse black holes that formed from gas clouds collapsing without ever passing through a stellar phase, with initial masses potentially reaching tens of thousands of solar masses, or they somehow circumvented the Eddington limit, accreting gas far faster than standard physics would normally allow. Neither of these scenarios is well understood. Neither of them sits comfortably within the existing theoretical framework, and the discovery that many of JWST's most alarming early galaxies are AGN hosts does not resolve the tension, it compounds it, replacing one impossible object with another, like lifting a stone and finding not nothing beneath it but a different equally baffling stone. There is, moreover, a population of early JWST objects that cannot be explained by AGN contamination because their spectral signatures are clean. JD's GSZ 14-0, the galaxy at redshift 1432 that we began this story with, is one of them. The team at the University of Arizona and Scuola Normale Superiore, who obtained its spectrum in January 2024 using JWST's NIRSPEC instrument, spent almost 10 hours integrating photons from that single object. What they found was unambiguous. The source is over 1/600 light-years across, physically extended in a way that a point source quasar cannot be. The light they were detecting was coming mostly from young stars, not from a central accreting black hole, and yet the galaxy is, in the words of the paper, several hundreds of millions of times the mass of the Sun. It is not a quasar, it is a galaxy. A genuine, star-forming, extended, massive galaxy, at a redshift of 1432, existing 290 million years after the Big Bang. And when they examined the spectra more carefully, they found something even more alarming than the galaxy's mass. They found oxygen. Oxygen is the third most abundant element in the universe today, but in the earliest moments after the Big Bang, it did not exist at all. In the first 3 minutes, the Big Bang produced only hydrogen, helium, and traces of lithium, all heavier elements, oxygen, carbon, nitrogen, iron, everything that makes up the material world as we experience it, were forged inside stars in the nuclear furnaces at stellar cores and dispersed into space by supernova explosions when those stars died. It takes multiple generations of stars to build up a significant abundance of oxygen in the interstellar medium. A star must form, live its entire life, which for a massive star is a minimum of several million years, and then explode, enriching the surrounding gas with the oxygen it manufactured in its core. A second generation of stars must then form from that enriched gas. This process is not instantaneous. It requires time, not the fleeting moments of particle physics, not even the short lifetimes of individual stars, but the accumulated product of multiple stellar generations, each completing its life cycle, dying and seeding the next, the detection of oxygen in JWST 14-0 at a redshift of 1432 means that this galaxy had already completed at least one full cycle of stellar birth, nuclear enrichment, stellar death, and gas re-enrichment, all within the first 290 million years of cosmic history. The galaxy had grandchildren before the universe was 3% of its current age. I will admit, when I first read this, I had to put down what I was reading and simply sit with it for a moment, because the implication is not just that this galaxy is more massive than expected. It is that the galaxy is more chemically evolved than expected, that it has lived on some level a more complete version of cosmic history than the timeline of the universe allows, if you plug in the numbers from the standard model. The JWST team who found the oxygen noted in their paper that its presence is a surprise and suggests that multiple generations of very massive stars had already lived their lives before we observed the galaxy. Multiple generations, each generation burning for millions of years. All of this happening before the universe had spent its first 290 million years. The oxygen detection was not made only by the JWST team. The Atacama Large Millimeter-Submillimeter Array in Chile, ALMA, one of the most sensitive radio telescope networks on the planet, also targeted JWST 14-0 and detected oxygen independently, confirmed by two separate research groups. The detection was not a fluke. The oxygen is there. This is what makes JWST 14-0 qualitatively different from the earlier wave of candidate massive galaxies. It is not a galaxy that merely looks more massive than expected, because we might be misinterpreting its luminosity. It is a galaxy whose chemical fingerprint tells a story of multiple stellar generations, and that story has a minimum duration built into it. The stars that made the oxygen had to form, burn for millions of years and explode. This is not an observation that can be explained away by adjusting the initial mass function or invoking AGN contamination. It is a hard constraint on how much stellar evolution had occurred before the moment we are observing, and it points inexorably toward a timeline that is difficult, perhaps impossible, to reconcile with the standard lambda CDM model in its current form. And in May 2025, before the scientific community had fully finished digesting the implications of JWST 14-0, JWST broke its own record, the Galaxy MOEM Z14, which stands with characteristic astronomers' humour for miracle of miracles, was confirmed at a redshift of 14.44, meaning its light was emitted when the universe was approximately 280 million years old, a mere 280 million years after the Big Bang. A paper describing it was titled, "With Admirable Straightforwardness, a Cosmic Miracle." This object exists at an epoch so early that the very phrase "the early universe" begins to feel inadequate as a description. 280 million years after the Big Bang, the universe had barely begun to produce the kind of complex multistellar environments we associate with galaxies at all. And yet here was MOM Z14, luminous, confirmed, and sitting at the very edge of what JWST can currently observe, daring the theorists to explain it. The accumulation of these discoveries has created a situation that cosmologists describe, depending on their temperament, either as a crisis or as an extraordinary opportunity. Both characterizations are accurate. It is a crisis in the sense that our best theoretical model is being systematically challenged at the extreme end of its predictions, and it is an opportunity in the sense that every anomalous data point is a clue, and the universe is currently handing us clues at a remarkable rate. But before we can evaluate what those clues mean, we need to ask a question that lives between the data and the theory. How certain are we of what we think we're seeing? The history of cosmology is full of apparent anomalies that dissolved on closer inspection. How confident are we that the impossible galaxies are actually impossible? This question has a complicated answer, and it pulls us directly into the most human part of this story. Most important thing to understand about the early wave of JWST galaxy discoveries is the distinction between two types of evidence: photometric redshifts and spectroscopic redshifts. Photometric redshifts are estimated from the colours of a galaxy as measured across multiple imaging filters. If a galaxy appears bright in some wavelength ranges and dark in others, you can use the pattern of that brightness distribution to infer how its light has been redshifted, which tells you approximately how far away it is. Photometric redshifts can be estimated quickly, applied to thousands of galaxies simultaneously, and are the primary technique used in the initial characterization of any deep field survey. Their limitation is that they are fundamentally indirect, relying on assumptions about the typical spectral energy distributions of galaxies, and they can be wrong, not by tiny amounts, by large amounts, in cases where a galaxy has unusual spectral properties or where a foreground galaxy at moderate redshift happens to have colours that mimic those of a very high redshift object. In the early months of JWST, when teams were reporting redshifts of z=17 and z=20 from photometric analysis alone, many experienced astronomers counselled caution. Photometric redshifts at these extreme values were not reliable without spectroscopic confirmation. Spectroscopic redshifts are a fundamentally different kind of measurement, a spectrum obtained by passing the galaxy's light through a diffraction grating and measuring the intensity of light at thousands of individual wavelengths, shows specific absorption and emission features: the hydrogen Lyman break, the Lyman alpha emission line, the oxygen emission lines, the Balmer series. Each of these features appears at a precisely known wavelength in the rest frame of the galaxy. When they are shifted to longer wavelengths by the expansion of the universe, the amount of that shift can be measured with extremely high precision, to within 0.1% or better. A spectroscopic redshift is not an inference, it is a measurement. The accumulation of spectroscopic confirmations over 2023 and 2024 was therefore enormously significant. JWST GSZ140 was not identified by photometry and left as a candidate. It was observed for nearly 10 hours with NIRSpec, and its redshift of 1432 was determined with what the team described as unambiguous evidence. The spectrum showed a sharp Lyman alpha break at exactly the position expected for z=14.32. It showed emission lines of ionized oxygen confirmed independently by ALMA. There was no reasonable interpretation of the data other than an extremely high redshift galaxy. So the confirmation landscape by mid-2024 looked like this: a small but growing set of spectroscopically confirmed galaxies at redshifts above z=12, all of which showed properties, mass, luminosity, chemical enrichment that exceeded lambda CDM predictions. A much larger population of photometric candidates at similar or higher redshifts, some of which would likely be revised downward when spectra were obtained, but the statistical pattern of which was robust enough that even accounting for all likely contamination, the overabundance of bright high redshift galaxies remained. The question of contamination is important and was addressed seriously by the community. A study led by Karthik Suresh at the University of Texas in 2023 showed that a significant fraction of photometric candidates at very high redshifts, particularly those without spectroscopic confirmation, might be imposters, galaxies at more moderate redshifts, typically z=2 to 5, whose unusual dust properties cause them to mimic the colour signature of a very distant galaxy. This is a real concern, and it means that the most extreme statistical claims about the abundance of very high redshift galaxies, claims based on photometry alone, should be treated with appropriate caution. But here is the crucial point: the contamination hypothesis can explain some of the photometric candidates. It cannot explain JWST GSZ14-0. It cannot explain MOMG14. It cannot explain the half-dozen spectroscopically confirmed galaxies at redshifts above z=12 that now anchor the observational case for anomalously early galaxy formation. These objects are not imposters, they are real, and they are a problem. There is a second calibration concern that deserves attention: the accuracy of stellar mass estimates. The mass of a galaxy cannot be directly measured. It has to be inferred from its observed brightness and colours, using models of stellar populations that relate the light a galaxy emits to the total mass of its stars. These models depend on assumptions about the initial mass function, the star formation history, the metallicity, the dust content, and the presence or absence of AGN emission. Each of these assumptions introduces uncertainty, and the uncertainties compound in ways that make mass estimates at high redshift notoriously imprecise. A galaxy whose estimated mass is 10 billion solar masses might plausibly have a true mass anywhere from 3 to 30 billion solar masses, depending on which set of assumptions you use. This uncertainty is not a dirty secret of the field, it is widely acknowledged, and it is one of the main reasons why many cautious cosmologists argued, in the early stages of the JWST era, that the apparent tension with lambda CDM might simply reflect our poor understanding of stellar population modelling at very low metallicities and very young ages, rather than any true violation of the theoretical framework. If the initial mass function in the early universe was weighted toward more massive stars, then early galaxies would be far more luminous per unit mass than our models assume, and we would systematically overestimate their masses from their luminosities. This is the top-heavy IMF hypothesis, and it is not absurd. There are theoretical reasons to expect that stellar populations in the extremely early universe, forming from nearly pristine gas with almost no metals, might have had an IMF skewed toward more massive stars. Population 3 stars, the very first generation of stars, forming from gas containing only hydrogen, helium and trace lithium, are predicted by theory to have been extraordinarily massive, possibly ranging from tens to thousands of solar masses. If some of the early galaxies observed by JWST contain a significant population 3 component, or if even their second and third generation stars formed in unusually massive configurations, the mass-to-light ratio could be very different from what modern stellar population models assume. The problem with the IMF hypothesis is that it is extremely difficult to test directly. We cannot resolve individual stars in galaxies at redshift 14. We cannot measure their masses directly. We can only infer population properties from integrated light, and those inferences are only as good as the models we use to make them. The IMF hypothesis is, as Megan Donoghue of Michigan State University has noted, an educated guess about the distribution of stellar masses in objects we have no direct way of resolving. And as one cosmologist quoted in a major review article phrased it, modifying the IMF to explain any troublesome observation you like is the domain of the wicked, because it introduces a free parameter that can be adjusted to fit almost any data, removing the predictive power of the theoretical framework. None of the cautionary notes, contamination, mass uncertainty, IMF variation, invalidates the JWST findings. They complicate them, as all good science should be complicated. They demand rigour and more data and more spectra and better models. But the core of the observational result, that JWST finds more bright, apparently massive galaxies in the early universe than the standard model predicts, and that some of these galaxies are spectroscopically confirmed to be at extraordinary redshifts, and to show signs of chemical enrichment that implies extensive prior stellar evolution, is not going away. It is hardening, year by year, into one of the most firmly established observational anomalies in modern cosmology. The question that matters now is not whether the anomaly is real, it is whether the anomaly requires us to change our model of the universe. And if so, how much, and in what direction? To explore that question properly, we need to spend time with the people who are actually doing this work, because the most important part of this story is not the galaxies themselves. It is the human beings who found them, the choices they made, the moments of doubt and excitement that accompanied every new data download, and the weight of a discovery that none of them had entirely expected. On the morning of the 12th of July 2022, a group of astronomers who had collectively spent decades waiting for this moment sat in front of computer screens, displaying data from an instrument they had, in many cases dedicated their careers to building, and looked at images of the universe that no human being had ever seen before. The emotion in the room, or more precisely, across the distributed network of shared Slack channels and video calls and email threads that served as the nerve centre of multiple JWST science teams, was not what you might expect from scientists who pride themselves on dispassionate objectivity. It was, by multiple accounts, something very close to euphoria. Kevin Hainline, an associate research professor at the University of Arizona and a member of the JWST team, described the moment when the first spectroscopic confirmations arrived as, oh my god, we did it, we did it, we did it." Researchers were freaking out in shared message threads. The word that appeared most often in the contemporaneous accounts of that period was not any scientific term but a simple, overwhelmed exclamation: "Wow, this is worth pausing on," because the people who built JWST, who fought for it through 2.5 decades of budget crises and design changes and political near-misses and technical nightmares, were not naive about the stakes. They knew this telescope could answer fundamental questions. They knew it was designed to peer at the edge of time, and yet even they, the people who had spent their working lives designing and testing and refining and launching this machine, were not fully prepared for what it showed them. Marcia Reek is a Regents Professor of Astronomy at the University of Arizona and the principal investigator of NIRCam, JWST's primary camera, the instrument that has produced many of the telescope's most spectacular and scientifically consequential images. She is sometimes called one of the founding mothers of infrared astronomy, having spent decades developing the detector technology that makes instruments like NIRCam possible. She began her involvement with what would become JWST in the mid-1990s, when the instrument was still at the conceptual stage and its launch was less than a dream, a hope, a proposal, a set of numbers on a whiteboard. She was still working on it a quarter of a century later, when it launched on Christmas Day 2021, and was still actively analysing data from it 3 years after first light. The NIRCam instrument that Reek led the development of has a design lifetime of 5 years. The telescope itself has a design lifetime of 10 years. The fuel load carried by the JWST launch vehicle managed so efficiently during the Ariane 5 launch that almost no mid-course correction burns were needed, gives the telescope a mission life that mission controllers now estimate could extend well beyond 20 years. Marcia Reek's instrument, her life's work in silicon and gold and engineering, may be observing the universe for longer than the entire time it took to build it. For the scientist who had spent the most of their careers waiting for this data, the experience of actually receiving it had a quality that does not fit neatly into scientific language. Ivo Labbe, speaking about the moment he first ran his analysis software on the red dots in the JWST image and saw the numbers return, distance 13 billion light-years, mass 100 billion solar masses, has described it not in terms of professional excitement but in terms of disorientation. He did not reach for a superlative, he reached for a negative. The impossible, not the extraordinary, not the unprecedented, the impossible. The word of a scientist who has spent his career building expectations based on a model he trusted and who has just been confronted with evidence that the model may not be adequate to the reality it was meant to describe. There is something deeply human in that moment. Science is not, as it is sometimes portrayed, a disinterested accumulation of facts. It is an activity conducted by people who have invested their professional identities, their years of training, their sense of what the universe is and how it works, into a framework they have tested and refined and trusted. When that framework encounters a genuine anomaly, not a measurement error, not a calibration problem, but a repeatable, spectroscopically confirmed, multi-team verified anomaly, the experience is not pure excitement. It is mixed with something more unsettling, a sense of the ground shifting, a recognition that a map you have trusted for decades may not fully describe the territory. And yet the people working at the frontier of this problem are not in despair. They are almost uniformly energized, because an anomaly is not a failure. An anomaly is the most valuable thing science can produce, because it tells you precisely where your understanding ends and the unknown begins. Brant Robertson of the University of California, Santa Cruz, who led several of the most important JWST Galaxy survey studies and contributed to the discovery of JWST GSZ 14-0, described the early galaxies not in terms of a crisis but in terms of a new tempo. The early universe changed rapidly in its first billion years, he said, with galaxies evolving 10 times quicker than they do today. He drew an analogy to a hummingbird, a small creature, but one whose heart beats so quickly that it is living a different life than other creatures. The heartbeat of these early galaxies is happening on a timescale that is simply unlike anything in the modern universe. This is a scientist not retreating from complexity, but embracing it, not dismissing the anomaly, but trying to find within it a new principle, a new understanding of how the universe can sometimes make things faster or efficiently at a different rhythm than the slow, hierarchical, steady-state average that our models had led us to expect. The story of how JWST came to be capable of showing us these galaxies at all is itself a story of extraordinary perseverance. The telescope was first proposed as a successor to Hubble in 1996, when it was envisioned as a 6-metre mirror with a cost of approximately $500 million and a launch date somewhere around 2007. By 2005, the mirror had grown to 6.5 metres, the cost had grown to $4.5 billion, and the launch had slipped to 2013. By 2010, the cost had grown to $6.5 billion. By 2011, a Senate subcommittee moved to cancel the telescope entirely, citing cost overruns and schedule delays. A massive lobbying effort from the astronomical community. Scientists writing letters, making phone calls, testifying before Congress, reversed that decision. By 2018, the cost had reached $9.7 billion, the launch had slipped to March 2021, and a congressional hearing described the project as having cost 19 times its original estimate with a 14-year delay. Northrop Grumman, the primary contractor, faced intense scrutiny and criticism. The project was, by any ordinary measure of project management, a disaster, and yet it worked. The telescope launched. It deployed without fault, it aligned without error, and it is now returning data that has changed, perhaps permanently, how we think about the beginning of the universe. Here is a number that puts the cost in perspective. The James Webb Space Telescope cost approximately $10 billion over 25 years, roughly $400 million per year. The United States defense budget in fiscal year 2022 was approximately $782 billion. The entire JWST program cost less than 5 days of American defense spending. For that price, we built a machine that can look 13.5 billion years into the past and photograph the first galaxies that ever existed. By any measure of what science has bought for its money in the history of human endeavour, this is extraordinary value. But the human story of JWST is not only about persistence and investment, it is also about a kind of intellectual courage, the willingness to look at data that contradicts your model and admit that the contradiction is real rather than explaining it away. This willingness has not always been universal. In the immediate aftermath of the first JWST deep fields in 2022, there was a predictable polarization in the cosmological community. On one side were researchers who argued that the apparent anomalies were real and potentially serious, that the excess of bright, early galaxies represented a genuine challenge to lambda CDM that could not simply be absorbed by adjusting model parameters within their permitted ranges. On the other side were researchers who argued that the anomalies were a product of measurement uncertainty, that photometric redshifts were unreliable, that mass estimates were systematically biased, that better calibration and spectroscopic follow-up would make most of the tension disappear. This debate was not conducted with perfect equanimity on either side. There were papers that overstated the case for a crisis. There were rebuttals that overstated the case for business as usual. There was some fraction of the discourse, primarily in social media and popular science media rather than in the peer-reviewed literature, that reached for the most dramatic possible framing, that spoke of JWST breaking cosmology or disproving the Big Bang, language that was at best imprecise and at worst actively misleading. The peer-reviewed science has been considerably more measured and considerably more nuanced. The picture that has emerged from 3 years of careful analysis is not lambda CDM is wrong, nor lambda CDM is fine, nothing to see here. It is something more complicated and more interesting than either of those simple narratives. Lambda CDM, in its standard form, is probably incomplete, but the nature and degree of its incompleteness are still being characterized, and the data we are now accumulating will eventually tell us in which direction we need to extend it. There is, at this moment, a group of astronomers at observatories and universities around the world, in Pisa, in Boulder, in Tucson, in Austin, in Jerusalem, in Cambridge, in Copenhagen, in Leiden, who are working on exactly that question. They are analysing spectra, running simulations, building new theoretical frameworks, and arguing with each other across preprint servers and at international conferences about what the impossible galaxies actually mean. They are, in a real sense, doing what scientists have always done when the universe refuses to behave. They are looking harder, thinking more carefully, and trying to build a better map of a territory that has turned out to be larger and stranger than anyone expected. The names that appear repeatedly in the papers, Labbe, Nelson, Carniani, Heinlein, Robertson, Rieck, Deckel, Finkelstein, represent a generation of astronomers who did not choose their careers knowing that JWST would transform them. They chose infrared astronomy and observational cosmology at a time when the best data available came from Hubble and Spitzer and ground-based facilities, when high redshift galaxy surveys were limited to tiny fields and shallow depths, when the edge of the observable universe was firmly behind a wall of uncertainty that no existing technology could pierce. They waited for decades, they built the instruments, they calibrated the detectors, and then the data arrived, and the universe handed them something none of them had entirely expected to find. I find this genuinely moving in a way that I struggle to articulate precisely. Not because the science is sentimental, but because the human story inside it is. These are people who spent the best years of their working lives preparing to look at something, and when they finally looked, what they saw was not confirmation but challenge, not the elegant completion of a model, but the ragged edges of its limits. And their response, almost uniformly, was not discouragement but acceleration, more data, better spectra, longer exposures, deeper surveys, because at the edge of what we know is not emptiness, there are galaxies there, old ones, big ones, chemically enriched ones, impossibly early ones. And every one of them is telling us something true about the universe that we haven't yet figured out how to hear. What are the stakes of figuring it out? That question is the one that has begun to keep theoretical cosmologists awake, not in despair, but in the specific restless excitement of people who sense that they are standing at the edge of a genuinely new understanding. To understand what is truly at stake in the JWST galaxy anomaly, you need to understand what lambda CDM is not just describing but underwriting. Lambda CDM is not a model of how galaxies form. That is a consequence of the model, but not the model itself. Lambda CDM is a model of the fundamental constituents of the universe, what the universe is made of, how much of each ingredient it contains, how those ingredients interact, and how the whole system evolves over time. It is, in the most literal sense, our best current description of physical reality at the largest scales, and it is built on a specific set of numbers, cosmological parameters, that have been measured with extraordinary precision over the past 3 decades. These parameters include the current expansion rate of the universe, known as the Hubble constant H0, measured to be approximately 67.4 kilometers per second per megaparsec by the Planck satellite's analysis of the cosmic microwave background, and approximately 73 kilometers per second per megaparsec by local distance indicators like Cepheid variable stars and Type Ia supernovae. The discrepancy between these two measurements, widely known as the Hubble tension, is itself a major open problem in cosmology, separate from the JWST galaxy anomaly but potentially related to it. They also include the current matter density, the dark energy density, the spectral index of primordial density fluctuations, and the optical depth to reionization. Each of these parameters has been measured with precision and the standard lambda CDM model is defined by the combination of all of them simultaneously. The impressive thing about lambda CDM is not that any one of these parameters is known precisely. It is that the entire set of them is simultaneously consistent with an enormous range of completely independent observations. The power spectrum of the cosmic microwave background anisotropies, the large-scale structure of the galaxy distribution, the abundances of light elements, the age of the oldest stars in our galaxy, the distance redshift relation of type Ia supernovae, the distribution of galaxy clusters as a function of mass and redshift, and many more. All of these different lines of evidence, pointing to the same set of numbers, give lambda CDM its remarkable persuasive power. When JWST finds galaxies at z=14 that appear too massive for the standard model to produce, it is not simply suggesting that we need to adjust our picture of how gas collapses into stars. It is poking at the entire edifice, because the rate at which galaxies can form is determined by the rate at which dark matter halos grow, which is determined by the amplitude and shape of the primordial power spectrum, which was set by inflation in the first fraction of a second after the Big Bang, and the rate at which the universe was expanding at z=14, which determines the age of the universe at that epoch, and therefore how much time the galaxies had to form is determined by the values of the cosmological parameters. If either of these things needs to change, then everything downstream of them changes too. Let us be concrete. One hypothesis that has attracted serious attention is the possibility that the amplitude of primordial density fluctuations, sigma-8, in the jargon, was higher than the standard CMB measurements suggest. If the universe at the time of recombination was slightly lumpier than Planck's data indicates, then dark matter halos would have grown faster in the first few 100 million years, allowing larger galaxies to form earlier. The problem with this hypothesis is that sigma-8 is one of the most precisely measured cosmological parameters, and any change large enough to resolve the JWST tension would cause other observable quantities, particularly the clustering of galaxies and the abundance of galaxy clusters at intermediate redshifts, to deviate from observations in ways that are not observed. You cannot simply turn up sigma-8 without breaking something else. Another hypothesis is that the dark energy driving the universe's accelerated expansion is not constant, not a cosmological constant as Einstein imagined it, but a dynamic field whose energy density varied over cosmic time. If dark energy was weaker in the early universe than it is today, the universe would have been somewhat younger at any given redshift, giving early galaxies slightly less time to form than the standard model calculates. This would actually worsen the tension, not relieve it. Conversely, if dark energy had been stronger in the early universe, a scenario sometimes called early dark energy, proposed originally to resolve the Hubble tension, the universe at z=14 would have been older than standard calculations suggest, giving early galaxies more time to assemble. This direction is promising, and there are papers pursuing it actively. The problem is that early dark energy models also affect the cosmic microwave background in ways that must be carefully tested against the Planck data. There is a third possibility that is more radical still, and which a minority of cosmologists are taking seriously enough to publish papers about. What if dark matter is not cold in the way the model assumes? In lambda CDM, cold dark matter means slow-moving particles. Particles whose thermal velocities in the early universe were negligible compared to the speed of light, and which therefore clustered effectively on all scales down to very small masses. But if dark matter is actually warm, if it consists of particles with somewhat higher thermal velocities, then small-scale structure would be suppressed in the early universe, and the first dark matter halos to form would be more massive, not less. This would actually change the mass budget available for early galaxy formation in a direction that could relieve the JWST tension. Warm dark matter models have been constrained by observations of the Lyman alpha forest and by galaxy surveys. Those constraints still leave open a range of particle masses that might be consistent with both the CMB data and the JWST findings. And then there is the most uncomfortable option of all. What if inflation, the theoretical process of exponential expansion in the first tiny fractions of a second after the Big Bang, which generated the primordial density fluctuations that seeded all subsequent structure, did something more complex than the simplest models assume? Standard single-field slow-roll inflation produces a nearly scale-invariant primordial power spectrum, a universe in which density fluctuations of all scales have roughly equal amplitude, but there are inflation models that produce enhanced power on specific scales, essentially making certain sizes of structure more probable from the very beginning of time. If such a model is correct, the very first dark matter halos might have been significantly more massive than the standard prediction, allowing the first galaxies to hit the ground running at a scale that standard lay CDM says is impossible. The implications of this last possibility are extraordinary. Inflation is not a small part of cosmology. Inflation is the theoretical scaffolding that explains why the universe is flat, why it is homogeneous on large scales, despite having regions that were never in causal contact with each other at the time of recombination, and why the primordial fluctuations that seeded all structure are distributed in the specific statistical pattern we observe in the CMB. If we need to modify inflation to explain the JWST galaxies, we are not making a small adjustment to a subsidiary model. We are reaching all the way back to the first microseconds of existence and revising what we think happened there. I find this genuinely haunting to think about. We built a telescope capable of looking 13.5 billion years into the past, to the edge of the universe's first few 100 million years, partly to test whether our model of those first few 100 million years was correct. And what we found is that the model may have problems not at the epoch we are observing, but at an even earlier time, at the moment of inflation itself, before any galaxy existed, before any star, before any atom, in the first 10 to the power of minus 32 seconds after the Big Bang. The James Webb Space Telescope, by looking backward through cosmic time, may be telling us something about events so ancient and so violent that they preceded everything we can directly observe. But before we get carried away, and the temptation is real because this is genuinely extraordinary stuff, we need to grapple with the full complexity of what the data actually says, and with the serious scientific arguments that pull back from the most dramatic interpretations, because there is a sober, well-grounded countercase to the cosmological crisis narrative, and it deserves thorough and honest examination. Let us start with a fact that is not in dispute. As of 2025, no individual JWST observation of a high redshift galaxy has been shown to be definitively, irretrievably inconsistent with lambda CDM in a way that cannot be accommodated by some combination of theoretical adjustments within the existing framework. This is not a reassuring statement for those who want the simplest possible answer to the question, is cosmology broken? It is, in a sense, exactly the kind of non-answer that science produces when it is working properly. When the evidence is real but the interpretation is genuinely uncertain, and when claiming more confidence than the data supports would be a disservice to the truth. Let me lay out the sober case in detail. It consists of several distinct lines of argument, each of which individually restrains enthusiasm for the most dramatic interpretations, and which together paint a picture that is considerably more nuanced than either lambda CDM is fine or the Big Bang is wrong. The first restraint comes from a careful analysis of what, precisely, we are measuring when we estimate galaxy masses at high redshift. A 2024 study led by Catherine Chwarowski at the University of Texas, which I mentioned earlier in the context of AGN contamination, provided the most systematic accounting of this effect to date. Working through the Sears survey data, one of the primary JWST datasets used for early galaxy studies, the team found that when AGN-contaminated sources were excluded from the stellar mass estimates, the remaining galaxies were broadly consistent with lambda CDM predictions. Finkelstein's conclusion was direct. There is no crisis in terms of the standard model of cosmology. This result is significant, but it does not fully close the case. The Kwarowski analysis applies most cleanly to the extreme mass outliers, the galaxies that most dramatically exceeded predictions, which turned out to disproportionately host AGN. A residual excess of massive galaxies remains even after AGN exclusion, and the excess of bright UV luminous galaxies at high redshift, the luminosity function problem, separate from the mass problem, is not resolved by the AGN explanation. The UV bright galaxies that define the overabundant bright end of the high redshift luminosity function are not all AGN hosts. Many are confirmed star-forming galaxies with clean spectral signatures, and they are still roughly twice as numerous as the model predicts. The second restraint comes from the inherent uncertainties in theoretical predictions. One of the lessons of the post-JWST era has been a humbling recognition of how imprecise our pre-JWST theoretical predictions actually were. The lambda CDM model is not a single unambiguous calculation. It is an umbrella under which many different simulation codes, semi-analytic models, and analytic approximations coexist, producing predictions that agree on the broad strokes but diverge significantly in the details. When multiple JWST teams asked, "Does this galaxy violate lambda CDM?" they were comparing their observations not to a single prediction, but to a range of predictions from different simulations which disagreed with each other by factors of 2 to 5 at the galaxy mass and redshift ranges in question. A 2022 study by Benjamin Keller at the University of Memphis compared the JWST spectroscopically confirmed high redshift galaxies against 4 major state-of-the-art cosmological simulations. The result was striking. All 4 simulations could produce galaxies as massive as the JWST detections at z equals 10. One simulation could produce them at z equals 13. 2 others could produce them at even higher redshifts, within the range of existing theoretical predictions, which is itself broad. The spectroscopically confirmed JWST galaxies were not necessarily in tension with lambda CDM at all. This is an important point that is often lost in the popular science coverage of these discoveries. The impossible galaxy narrative assumes that lambda CDM makes a precise, single-valued prediction for the maximum mass of a galaxy at a given redshift, and that the JWST galaxies exceed that prediction. But lambda CDM does not make a single-valued prediction. It makes a probability distribution, and the question is not, can this galaxy exist, but how probable is it? A galaxy that lies at the 5th percentile of the predicted distribution, meaning that only 5% of lambda CDM universes would produce such a galaxy in that region of sky, is surprising, but not impossible. A galaxy at the 0.1 percentile is more worrying. The difference matters enormously, and quantifying it precisely requires both better theoretical predictions and better observational statistics. The third restraint is perhaps the most philosophically interesting. The IMF, the initial mass function describing the distribution of stellar masses in a newly formed stellar population, is one of the foundational assumptions of stellar population modelling, and its universality has been a cornerstone of observational astronomy for half a century. But universality is an assumption, not an observation. We have measured the IMF carefully in the solar neighbourhood, in young star clusters in the Milky Way and the Magellanic Clouds, and in a handful of nearby galaxies. At high redshift, in environments that are denser, more metal-poor, and more energetically extreme than anything in the local universe, there is no direct measurement of the IMF at all. If the IMF in the early universe was indeed top-heavy, skewed toward more massive stars, the consequences extend beyond simply explaining why early galaxies appear more luminous than expected. A top-heavy IMF would produce more ultraviolet radiation per unit stellar mass, which would affect the reionization of the universe during the epoch of reionization. It would produce more supernovae per unit stellar mass formed, which would change the chemical enrichment history of the early interstellar medium. It would produce more massive stellar remnants, black holes and neutron stars, earlier potentially explaining the overabundance of massive black holes in early galaxies that we mentioned earlier. A single change to the IMF would ripple through the entire picture of early galaxy formation, changing many things simultaneously. This is either deeply unsatisfying, because it is hard to test, or deeply exciting, because if confirmed, it would represent a fundamental extension of our understanding of how stars form in extreme environments. A paper published in 2025 explaining the two massive high-redshift galaxies in JWST data modelled the effect of a non-universal IMF in early galaxies and found that it could, in principle, explain much of the apparent tension with lambda CDM without requiring any modification to the underlying cosmological model. The paper has attracted significant interest, though its central claim has not yet been confirmed observationally. The fourth restraint is the most interesting, and brings us to the frontier of ongoing research. Over the past 2 years, a small but growing number of theorists have been working on what is perhaps the most compelling resolution of the JWST tension that does not require modifying lambda CDM, the feedback-free starburst mechanism proposed by Avishai Dekel and colleagues at the Hebrew University of Jerusalem. The central insight of the Dekel model is this. In the very early universe, the gas available to form galaxies was denser, less chemically enriched, and cooler in relative terms than gas in the modern cosmos. Crucially, it was also operating in an environment where the typical free-fall timescale, the time it takes gas to collapse under gravity, was shorter than the timescale for massive stars to develop the radiative winds and ionizing radiation that normally disrupt star-forming regions and terminate the conversion of gas into stars. In the local universe today, the free-fall time in a dense molecular cloud is typically a few million years, and massive stars begin their disruptive feedback within 1 to 2 million years of their formation. The two timescales are comparable, and the result is that stellar feedback limits star formation efficiency to a few % per free-fall time. In the early universe at very high redshift, the density of gas was higher and the metal content was lower. The free-fall time was shorter, potentially shorter than 1 million years, while the feedback timescale remained similar. This means that in the earliest, densest protogalactic structures, the gas could collapse into stars and complete an entire burst of star formation before the resulting massive stars had time to launch the winds and radiation that would blow the remaining gas away. The starburst ran to completion, unchecked by feedback, at efficiencies approaching 100%. The Dekel feedback-free starburst model makes specific, testable predictions. It predicts a characteristic size for these starburst regions, very compact, dense stellar systems. It predicts specific stellar population signatures. It predicts an excess of very UV-bright galaxies at Z greater than 10, which is precisely what JWST observes. And it requires no modification to lambda CDM whatsoever, no new dark matter, no new dark energy, no modified inflation. It simply proposes that under the specific physical conditions of the earliest cosmic epoch, star formation ran more efficiently than it does in any modern galaxy we have observed, for reasons grounded in well-understood physics. The model is not yet confirmed. The observational tests required to validate or refute it are still underway, but it represents exactly the kind of creative, physics-grounded theoretical work that an anomaly like the JWST overabundance demands. Not a retreat to cosmology must be wrong, nor a dismissal of the data must be right, but a careful search for physical mechanisms that are consistent with both the new observations and the existing framework. And there is a fifth possibility that the community has been wrestling with since early 2023, and which may ultimately prove to be the most important of all, that what JWST is seeing is not one thing but several things, all present simultaneously. The excess of bright high redshift galaxies is real. Its causes are probably plural. AGN contamination accounts for some of the most extreme mass outliers. A top-heavy early IMF may contribute to the apparent luminosity excess. Feedback-free starbursts may account for a portion of the true star formation efficiency enhancement, and some small residual tension with lambda CDM, requiring either a modification to the primordial power spectrum, a change to the early dark energy density, or an extension to our model of dark matter, may remain even after all these astrophysical effects are properly modelled. The universe, as it has a habit of doing, is refusing to give us a single clean answer. It is giving us a multi-dimensional, interrelated set of puzzles, each of which touches on a different part of our theoretical framework, and all of which must be solved simultaneously. There is, in the history of science, a recurring pattern. A new instrument opens up a new domain of observation. Initial data produces dramatic results that seem to overturn existing models. The community divides between advocates of revolution and advocates of conservation. Careful analysis reveals that the truth is more complicated than either faction initially claimed. That the existing model is resilient but imperfect, that new physics is suggested but not yet proven, and that the work of science is to characterize the imperfection precisely enough to know which direction to extend the model. This happened with the Hubble Space Telescope, which initially seemed to produce ages for globular clusters that exceeded the age of the universe, a scandal that was eventually resolved by refinements in both distance measurements and model assumptions. It happened with the original discovery of dark energy in 1998, which was initially greeted with skepticism and is now the cornerstone of the standard model. It is happening now with JWST. The difference this time is the scale and speed of the data. JWST has produced more spectroscopically confirmed high redshift galaxies in 3 years than Hubble produced in 30. The pace of discovery has been extraordinary, and the cumulative weight of the data, not the single most dramatic outlier, not the most alarming individual result, but the consistent repeatable pattern across hundreds of confirmed objects, is not going away. Here is where we stand as of 2025. The broad outlines of lambda CDM remain intact. The universe is 13.8 billion years old. The Big Bang happened. Dark matter exists. Dark energy is real. The hierarchical assembly of structure from small-scale density fluctuations is the correct general description of how cosmic structure forms. None of this is in serious doubt. What is in serious doubt is whether the standard form of lambda CDM, with its specific assumptions about star formation physics, dark matter properties, the initial mass function, and the primordial power spectrum, is fully adequate to explain what the universe produced in its first few 100 million years. The evidence from JWST says, with growing confidence, that something happened in that first epoch that we did not fully anticipate, and that understanding it will require at least some extension, possibly a significant extension, of the theoretical framework we have trusted for 3 decades. The nature of that extension is still unknown. That is not a failure. That is the current location of science. The story of the JWST impossible galaxies is not finished. It is not even close to finished. It is, if anything, in its early stages, the moment in a long investigation when the first crucial evidence has been gathered, the initial hypotheses have been proposed and partially tested, and the direction of future inquiry has been sketched out. But the resolution is still years or decades away. This is worth dwelling on for a moment, because the timescale of science is so different from the timescale of news. When JWST images are released and the internet lights up with "Scientists Break Cosmology" headlines, there is an implicit promise of resolution, of a final answer that will either confirm or deny the crisis within weeks or months. Science does not work this way. Science works by accumulation, by building an ever larger and more precise body of evidence until the weight of it forces a consensus. The JWST galaxy anomaly will be resolved, eventually, but the resolution will take years, and it will involve a combination of new observations, new theoretical models, and new instruments that do not yet exist. Let us talk about what those next steps look like. The most immediate priority is obtaining spectra for a larger sample of high redshift galaxy candidates. As of mid-2025, the number of spectroscopically confirmed galaxies at Z greater than 10 was still relatively small, in the dozens rather than the hundreds. Each additional spectrum provides an independent test of the redshift estimates, constrains the galaxy's physical properties, and adds a data point to the statistical characterization of the high redshift galaxy population. JWST's near-spec instrument, with its multi-object spectroscopy capability, allowing spectra of up to 100 objects to be obtained simultaneously, is running targeted programs to expand this sample as rapidly as possible. The JWST program alone had logged hundreds of candidate galaxies from the first year of operation and was systematically obtaining spectra of the highest priority targets. Deeper photometric surveys are also crucial. The overabundance of bright UV galaxies at high redshift is, statistically, better characterized from photometry than from spectra, because photometry can survey large areas of sky and build up statistically meaningful samples across a wide range of luminosities. JWST's Pure Parallel program, which uses the telescope's instruments to observe secondary targets while the primary scientific program is underway, essentially getting free data from the telescope's slew and guide time, has been accumulating additional deep field data that will help quantify the high redshift galaxy number counts with greater precision. Perhaps most importantly, the coming years will see the first results from the Nancy Grace Roman Space Telescope, NASA's Wide Field Infrared Space Observatory, currently in development, with a planned launch in the late 2020s. A JWST is a precision instrument with a narrow field of view. Roman is a survey machine. Its wide field instrument covers an area of sky approximately 100 times larger than JWST per pointing, allowing it to observe hundreds of millions of galaxies across billions of light-years of cosmic volume. Roman will not replace JWST. It cannot match JWST's sensitivity or resolution for individual objects, but it will provide the statistical context that JWST currently lacks. When Roman surveys billions of galaxies and maps their distribution, clustering, and abundance as a function of redshift, it will provide tight constraints on the cosmological parameters that govern structure formation, helping to determine whether the JWST high redshift anomaly requires a modification to those parameters. The combination of JWST and Roman is, in a very real sense, the observational cosmology equivalent of having both a microscope and a wide-angle camera pointed at the same problem simultaneously. JWST goes deep and narrow, resolving individual galaxies at extreme redshifts and characterizing their physical properties in detail. Roman goes wide and shallow, mapping the statistical distribution of galaxies across vast cosmic volumes and constraining the cosmological framework within which those individual galaxies exist. Together, they may finally allow the field to distinguish between the astrophysical explanations for the JWST anomaly, modified star formation physics, IMF variation, AGN contamination, and the cosmological explanations, modified dark matter, modified dark energy, modified primordial power spectrum. On the theoretical side, the next few years will see significant advances in simulation capabilities. Current state-of-the-art cosmological simulations, programs like Illustris TNG, Simba, FIRE, and Eagle, model the formation of galaxies in volumes of space tens to hundreds of megaparsecs across, following billions of particles and attempting to capture the relevant physics of gas dynamics, star formation, stellar feedback, and black hole growth. These simulations have been invaluable for testing lambda CDM predictions, but they have limitations. Their spatial and mass resolution is insufficient to capture the detailed physics of star formation in the very first galaxies, and their volume is often too small to contain a statistically significant sample of the most massive and luminous objects at very high redshifts. A new generation of simulations, some of which are already underway, will improve on both counts. Programs specifically designed to simulate cosmic dawn, the first few hundred million years of galaxy formation, are being developed with higher resolution or sophisticated stellar and black hole physics, and a greater focus on the physical processes that the JWST data suggests are important. Feedback-free starbursts, population-3 stellar evolution, early AGN growth, and the complex interplay between star formation and chemical enrichment in extremely metal-poor environments. The predictions from these next-generation simulations will provide much sharper tests of the competing hypotheses than anything currently available. There is also the tantalizing prospect, still speculative but not absurd, of JWST detecting the signature of population 3 stars directly. These are the very first stars that ever formed in the universe. The ones that ignited from nearly pristine hydrogen and helium gas at the end of the cosmic dark ages, before any heavy elements existed to influence their formation. Population 3 stars are predicted to have been extraordinarily massive, burning hot and bright and dying violently in supernovae and pair instability explosions that dispersed the first heavy elements into the surrounding intergalactic medium. They are, in a very direct sense, the origin of almost every atom in your body heavier than helium. Without population 3 stars, there would be no carbon, no oxygen, no iron, no calcium, no chemistry complex enough to produce life. We have never definitively detected a population 3 star, or even a galaxy whose light is dominated by population 3 stellar emission. The closest we have come are tentative hints in a handful of JWST spectra of highly magnified, very metal-poor galaxies at moderate redshifts, objects that show emission line ratios suggestive of extremely hot, massive, metal-free stars, but which have not yet produced a conclusive confirmation. In April 2026, a team announced what they described as the strongest evidence yet for population 3 stars in a high redshift system, though the claim awaits independent confirmation at the time of writing. Finding a confirmed population 3 galaxy, or even a star cluster, would be one of the most consequential astronomical discoveries in history, closing the last observational gap in the story of cosmic chemical evolution and validating decades of theoretical predictions about the nature of the first stellar generations. The search for population 3 stars is, in a real sense, connected to the galaxy anomaly problem, because both involve understanding what happened in the very first few 100 million years after the Big Bang. If the first stars were indeed extremely massive and formed in dense clusters that quickly self-enriched with heavy elements, the transition from population 3 to population 2 stars, from pristine primordial gas to the enriched environments that characterize all subsequent star formation, may have happened faster than previously modelled. Fast chemical enrichment would mean that the conditions for more rapid, efficient star formation that characterize the feedback-free starburst model might have been in place earlier, and for a shorter period than current estimates allow. This in turn would affect our interpretation of the overabundant bright galaxies at cosmic dawn. Everything connects to everything else, which is both the joy and the frustration of working at this frontier. And then there is the Hubble tension, that persistently annoying discrepancy between the expansion rate measured from the early universe via the cosmic microwave background and the expansion rate measured from the local universe via Cepheid variables and supernovae. The tension has reached the level of 5 sigma, the gold standard for significance in particle physics, and has not resolved despite decades of effort to find systematic errors in one or both measurements. If the Hubble tension reflects a genuine incompleteness in lambda CDM rather than an unidentified systematic error in the measurements, it suggests that the expansion history of the universe is not quite what the standard model predicts. And if the expansion history is slightly different from standard, whether due to early dark energy, dynamic dark energy, or some other modification, then the ages of early galaxies at a given redshift are also slightly different from standard calculations. A universe that expanded slightly differently in its first few 100 million years would be slightly older at z equals 14 than standard lambda CDM predicts, giving early galaxies a little more time to form, not necessarily enough to resolve the full anomaly, but potentially enough to bring some of the apparent tension into the range of astrophysical explanations. The interplay between the JWST galaxy anomaly, the Hubble tension, and the constraints from the cosmic microwave background forms the central problem of observational cosmology in 2025. These are not 3 separate problems. They may be 3 different symptoms of the same underlying issue, a single gap or imprecision in our model of the universe that we have not yet correctly identified, which is manifesting simultaneously in multiple different observational contexts. Finding the thread that connects them and pulling it may be what ultimately brings the next major advance in fundamental physics. It is also possible, and this is a possibility that is worth stating plainly, that the answer will not be a single dramatic revolution in our understanding. It may be a succession of smaller revisions, a better model of early star formation here, a more accurate initial mass function there, a minor modification to the early dark energy density, a slightly revised primordial power spectrum. Science, in practice, rarely delivers the clean paradigm shifts that retrospective histories make it appear. More often it delivers a gradual refinement, a progressive improvement in the accuracy of the map, a steady reduction in the size of the remaining blank spaces, each generation of scientists pushing the frontier a little further without ever quite arriving at the final answer, because the final answer is always more complex than the current best approximation. There is a version of the JWST Galaxies story that ends with Lambda CDM was right all along, we just needed to model the astrophysics better. There is another version that ends with Lambda CDM needed a specific modification to the primordial power spectrum, and finding that modification told us something important about the physics of inflation. There is a third version that ends with the early universe formed stars so differently from the modern cosmos that it behaved, in a very real sense, as a different kind of universe, one governed by the same fundamental laws, but expressing them in ways we had not anticipated. Each of these versions is possible. Each of them is, in a sense, already supported by some portion of the existing evidence, and each of them would represent a genuine advance in human knowledge, even if none of them delivers the dramatic everything we thought we knew was wrong moment that makes for compelling headlines. The James Webb Space Telescope has not broken cosmology, but it has done something arguably more valuable. It has shown us precisely where the edges of our knowledge are, pointed at the cracks in our model with extraordinary precision, and given us enough data that we can, for the first time, hope to characterize those cracks well enough to begin filling them. The cracks are real, the filling will take years, and the result will be a better map of the universe, one that extends our understanding of what the cosmos is and how it came to be further into the darkness than we have ever seen before. The edge of time is not empty. There are galaxies there, old ones, massive ones, chemically complex ones, ones that should not exist but do, and they are waiting for us to understand them. There is something that I keep coming back to when I think about JWST GSZ 14-0. Not the statistics, not the spectroscopic redshift of 1432, not the inferred mass of several hundred million solar masses, not the chemical signature of multiple stellar generations that should have been physically impossible to complete in the time available. What I keep coming back to is the light itself. The photons that JWST collected from that galaxy, the actual electromagnetic radiation that struck the mirror's golden beryllium surface and triggered the detectors of NIRSpec in January 2024, were emitted from stars that burned and died before our solar system existed, before any rocky planet had formed in the Milky Way, before the clouds of gas that would eventually collapse into our Sun had so much as begun their slow gravitational concentration. Those photons have been travelling through expanding space for 13.4 billion years, surfing the universe's growth, stretching from visible light into the deep infrared as the cosmos expanded around them, finally arriving at a mirror we placed in space, built by the species that descended from the dust. Those photons once illuminated, there is something in that thought that resists ordinary description. We are, in a sense that is not metaphorical but physically literal, looking at the universe's adolescence and trying to understand it from the vantage point of its old age, using instruments that the universe itself built, because we are part of the universe, and our instruments are made of atoms forged in stars, and our understanding is the universe's way of reflecting on itself. And what we find, when we look that far back, is not the simple, sparse infant cosmos we expected. We find complexity, mass, and chemical maturity that arrived far sooner than our best models said they could. We find galaxies that were already ancient when our sun's precursor dust had barely condensed. We find oxygen, the breath of future civilizations, already present in a universe just 290 million years old, forged and dispersed by stellar generations that burned and died in a cosmic eye blink. This does not mean the Big Bang is wrong. It does not mean the universe is older than 13.8 billion years. It does not mean dark matter is a fiction, or that Einstein's equations need to be thrown out. What it means is something more subtle and more interesting than any of those dramatic conclusions. It means that the early universe was better at making things than we thought. It was more energetic, more efficient, more creative in its first few 100 million years than any of our simulations had suggested. And our job now, the job of the scientist who will spend the next 10 years analysing JWST data, running better simulations, developing new theoretical frameworks, launching new telescopes, is to understand how. The generation that built JWST asked whether the universe's first light could be seen. The answer, as of 2025, is yes, and the light is telling a story we do not yet fully understand. The generation that comes after them will need to learn to read that story. Not the generation that discovered the anomaly, but the one that resolves it. Not the astronomers who first saw JD's GSZ 14DSO and gasped at what it was, but the theorists who will eventually explain why it exists, and in explaining it, will extend our map of reality into a region it has never before reached. Every scientific question worth asking points beyond itself. The better we understand the early universe, the more clearly we can see the boundary of what we do not yet understand, which lies always at the next redshift, the next spectral line, the next detection at the limits of what any instrument can resolve. JWST's successor is already being discussed. Concepts for infrared observatories that could detect galaxies at z=20, a mere 180 million years after the Big Bang, exist on paper, waiting for the budget allocations and the political will and the decades of engineering work that brought JWST from whiteboard to orbit. Each generation of telescope pushes the frontier a little further. Each frontier reveals a new anomaly. Each anomaly points toward a deeper question. The universe is not obligated to fit our models. It has never been obligated to fit our models. It is under no compulsion to be simpler than it is, more predictable than it is, or more comprehensible than it is. The history of astronomy is a history of humans discovering repeatedly that the universe is more complex, more vast, more ancient, and more strange than the best available description of it allows. And every time we made that discovery, we built a better description and a better instrument to test it, and looked again with finer eyes. We are in that process now, right now. In real time, the galaxies at the edge of time are waiting. The model has cracks that the data has found. The theorists are working. The next spectrograph is being calibrated, and somewhere in a university office at 3 a.m, looking at a plot that doesn't fit the model quite right, there is a person who will eventually figure out why, and in figuring it out, will take the next step in the oldest human project there is, the project of looking up, and asking what is really there. We are the generation that built the mirror. The answer belongs to whoever uses it next.